Hi everyone, I'm back for our second part of the hemodynamic pressure and calculation tutorial. What we're going to do this time is look at more equations. So I have some in here to see. At the top, I actually wrote in the hydrolysis equation. We'll look at this again next week when we start looking at arterial blood gases, but I thought it would make for a good review. The hydrolysis equation refers to the hydrolysis of carbon dioxide in our blood as it combines with water. Of course, water is the major constituent of blood, and that forms a compound called carbonic acid. If you can see these numbers, if you add CO2 to H2O, you'll get H2CO3. That's the carbonic acid. So there's two H's, your two hydrogens from water, your one C, there's your carbon, and you got three O's, which are your two oxygens from carbon dioxide and your one from water. So we're simply adding those, essentially adding those atoms together. It dissociates into a hydrogen ion and then bicarb molecule. So if we take carbonic acid, H2CO3, it will dissociate, it'll split into a hydrogen ion plus bicarb. You can see if you take bicarb and add the hydrogen back to it, you've got the carbonic acid. So the hydrogen ion is where we get the acidity from our pH, which we'll look at next week. But you also see bicarb being produced. So that's very important. And that's the kind of the take-home message from this hydrolysis equation that we're looking at today. Therefore, the more carbon dioxide we produce by metabolism, the more bicarb that's produced. So as your CO2 increases, bicarb increases, and that's naturally occurring within the blood via the hydrolysis equation. Or conversely, as your CO2 is decreased, then we have less bicarb. And this is a buffering mechanism. We know that bicarb buffers the acidity that's coming from the carbon dioxide. So it's kind of nice to know that as we produce more carbon dioxide in the blood and our pH goes down, that we're buffering that decreased pH from the bicarb that's being produced through this hydrolysis equation. So I have that this is buffering, not compensation. Remember, when we compensate in our blood gases, we're looking at organ compensation. Either the lungs are compensating or the kidneys are compensating. So this is a point that we'll look at next week. But I thought it would be just a good idea to go over the hydrolysis equation early. Here's our hemodynamic loop again. I'm going to look at four different equations. One is the cardiac output equation. And we'll practice these later in upcoming units. But this is just to put our eyes on it again. Cardiac output can be quantified using the modified Fick equation, which is the oxygen consumption, V dot O2, oxygen consumed here at the tissues, which is approximately 250 milliliters per minute. I'm not worried about the unit of measures right now. We'll look at that in the units. We'll take oxygen consumption, divide by the CaO2 minus the CvO2. So your CaO2 is coming from this side of the hemodynamic loop. That's your arterial oxygen content. And we're subtracting CvO2, which is from this side of the loop. So we have arterial oxygen on this side and venous oxygen on this side. Of course, because blood is moving in that direction. So if we take our oxygen consumption, which is approximately 250 mils per minute, and divide by our AVO2 content difference, normal CaO2 is around 20. Normal CvO2 is approximately 15. So 20 minus 15 gives us 5. And then we're going to multiply that by 10, which is a constant. 5 times 10 is 50. 250 oxygen consumption divided by CaVO2 content of 5 times a constant of 10. 250 divided by 50 equals 5 liters per minute. 5 liters per minute is what we're looking for, cardiac output. So that's a pretty neat equation. Second equation, stroke volume. As the heart contracts, it could be the right heart or the left heart. Hopefully they're both the same. The stroke volume is the volume of blood that's being emptied by the ventricle upon each contraction. So a simple way to calculate stroke volume is to take the cardiac output that we've already defined up here, divide by heart rate. We know this already. So I took 5 liters, turned it into 5,000 milliliters, divided by a heart rate of 80 beats per minute, and a stroke volume of 62.5 milliliters is the answer for this problem. I'm going to take the stroke volume and determine the ejection fraction. The ejection fraction is the total amount of blood that is within the ventricle at end diastole. So remember, diastole is relaxation. So at the very end of relaxation, which is the largest that the ventricle is going to open, we can measure that volume. And I'll put 100 mils just to make the math easy. As the ventricle contracts, it doesn't eject all of its blood from the ventricle, just a part of it. There's a little bit left behind, keeping the ventricle open. So for ejection fraction, I take the stroke volume and I put it over the end diastolic volume. So the stroke volume of 62.5 over over the end diastolic volume of 100 mils. That's just arbitrary, just to make the math a little easy. Gives us 62.5%, roughly 2/3, which is a normal ejection fraction, around 2/3 to 3/4 of what the ventricle can hold. So that's a pretty normal number. Lastly, we'll look at pulse pressure. Pulse pressure is the systolic minus the diastolic pressure. So I have a normal arterial BP of 120/80, and the difference is 40 torr. So pulse pressure is the difference between the systolic and the diastolic. If you have any questions, please let me know. This one is a pretty easy sheet to cover. It helps you understand, if needed, helps you understand what an index is referred to. With hemodynamic values, we can look at an index value for that particular patient, which is whatever the variable it is that we're describing, divided by that patient's body surface area. And again, just to make things easy, typically we'll use a body surface area of 2 meters square. And when we get to this in our upcoming unit, we'll actually look at a body surface area chart and find out what our own body surface area measurement is. But this is just to help get the concept across. What I've taken is, as a variable, is the cardiac output, 5 liters per minute for this person, and a cardiac output of 5 liters per minute for this person. This person is supposed to look taller than this person. So this person, this taller person, would have a larger body surface area up here than this person. And again, to find the index of whatever it is that we're solving for, we take the variable, which is the cardiac output in this case, of 5, and we divide by the body surface area of 2. This patient has a body surface area larger than this patient. So this patient, I gave a body surface area of 2.5. So even though this patient and this patient share the same cardiac output value, when you look at the cardiac index and solve the math, this patient's cardiac index is a 2.5, this patient's cardiac index is a 2.0. Okay? So what this does is it makes the cardiac output relative to the size of the individual. Even though these two people have the same cardiac output, they have differences in their cardiac index, which again is more relative to their size. So it's actually, even though we talk about cardiac output a lot more, it's actually a more valuable number to look at that cardiac index, because that tells you how well that patient's cardiac output is matching the metabolic demands of that particular size patient. Again, we'll cover this later in an upcoming unit, but this is just to remind us of that type of information. This sheet with a lot of stuff on it is just a quick review. I'll have all of this loaded in Canvas for you so you can look this over. But it's a hemodynamic loop. It has all the values in it. It has abbreviations of the names. You'll see the different calculations with hydrolysis and body surface index at the top. I hope this has been a good review for you. Again, if you have any questions, please let me know. Thank you.